In this video, we're going to talk about oligopoly, and we're going to spend all of our time talking about game theory. So when you think about oligopoly, there are different models of oligopoly. So we've looked at the model of perfect competition and monopoly and monopolistic competition. There are models like that for oligopoly, but we're not going to go into those. If you're interested in those, I've got videos for a class called Industrial Organization, and you can find videos on the different market or the different models of oligopoly there. Here, what I want to do is I want to focus more on the game theoretical investigation into oligopoly. When you start talking about oligopoly, remember an oligopoly is a market share or a type of market where there are very few firms so that each firm has a large market share. We've talked about perfect competition. Each firm is small compared to the size of the market. Monopolistic competition. Each firm is small compared to the size of the market. Monopoly, where there's only one firm and it is one whole side of the market. Now we're talking about a situation where there are just a few firms. Maybe there's two. We would call that a duopoly. Or maybe there's 5 firms. But when there's just a few firms, then each firm is going to be what we would call big compared to the size of the market. If there's 2 firms and they're roughly the same size, they would each have about half the market share. What that means is, so if each firm is small compared to the size of the market, then the firm doesn't need to worry about what the other firms are doing. Now, the behavior of the other firms will impact each individual firm, but only because of what ends up happening in the market. If you're one of only 2 firms, then the behavior of that other firm is going to have a huge impact on you. So if I'm a firm and you're a firm, then my behavior is going to have a big impact on the market conditions that you're going to be operating in. And so in order to make the best decision, in order to maximize profit, you need to form some expectation about what you think I'm going to do. And what I do is going to be dependent upon what I think you're going to do. And so we're thinking about firms strategically interacting. And that is the area that we call game theory. It's just the study of strategic interaction between people, whether or not those people are acting on behalf of a firm or just 2 people interacting. It's called game theory. In my opinion, it's one of the more interesting sub-disciplines within the field of economics. And when you're talking about game theory, there's kind of a setup that we need, and the setup is we'll be talking about players. We're talking about games here, but don't think of this as games in the fun sense, right? These aren't necessarily going to be fun games. But we'll analyze these strategic situations by thinking about the firms or the individuals involved in the game as being players. So you're going to have players. Each player is going to have some strategies. So these strategies might be what price they choose to charge in the market. Maybe they charge a low price or a high price, or whether or not they advertise, or whether or not they enter a market or don't enter a market. So those are going to be strategies. And then there are going to be payoffs for each player. And the payoff that each player gets depends obviously on the strategies that are chosen by the 2 players or 3 players. We're going to be thinking about simple games, but we can make, and it's easiest to start out if you think about 2 players, but you could have 100 players. The game obviously gets much more complex, so we won't be doing anything like that. So we'll think about players, strategies, and payoffs. And then there are a couple of other dimensions we've got to think about. The order in which the players make decisions is important. So the players might make their decisions simultaneously. So you might have to form a guess about what you think the other player is going to play or do, and then go ahead and decide what you're going to do, and then the game is played, and then you find out what the other player did. Or you could have what we would call a sequential game, where one player goes first, and then the other player gets to react to what that first player did. So there's a first mover and a second mover. And then we can think about how long the game is played. So you could have maybe a one-shot game, a game that's played one time, or you could have a game that's repeated indefinitely, an infinite game, or you could have a game that's repeated for maybe 10 periods. And we'll think about how the length of the game affects the way the game is played. Let's start by thinking about the simplest version, and that would be what we would call a simultaneous move one-shot game. So this will have two players, and the game's going to be played one time, and they have to make their decisions simultaneously. Neither player gets to see what the other player is going to do. And we're going to think about what we call a normal form of the game. A lot of times I call this a game matrix. There's another form of the game that we'll think about here in just a little bit, but we'll start here because this is the simplest version. So this is the normal form of the game. We'll talk about players A and B, and let's talk about the strategies. So if we think about player A has two strategies. Those are going to be either up or down. Up or down. And then we're going to have player B, and player B can choose either left or right. So each player has two strategies. Now we're going to create what I always refer to as the game matrix, and that's going to be simply a box. The word matrix in this context is used in the same way that it would be used in a matrix algebra class or a linear algebra class, where you've got a matrix that has rows and columns. Okay, so we're going to think about a matrix here with two columns and two rows. So we're going to divide it into our two rows and our two columns. We're going to put player A right here and player B up here. These two rows are going to correspond to player A's two strategies, which are they can either choose up or down. Player B also has two strategies. They can choose left or right. And then we're going to think about the cells of this matrix, and we're going to divide these cells in half diagonally, each cell, and we're going to put the payoffs. So for example, if player A chooses up and player B chooses left, then we're in this cell, and let's suppose that the two payoffs are going to be that player A will put player A's payoff in the bottom left-hand corner of each cell, and we'll put player B's payoff in the top right corner. Let's suppose if A chooses up and B chooses left, then A gets 10 and B gets 20. And you can think about those as dollars. We'll think more about that later. On the other hand, let's suppose A chooses up and B chooses right, then in that case, A is going to get 15 and B gets 8. Or if A chooses down and B chooses left, then we're down here. Let's suppose that A loses 10 in that case and B gets 7. And then if A chooses down and B chooses right, let's suppose they each get 10. So there's our game matrix. And what we want to do is we want to say, okay, well, we need to think about what's the likely outcome. When we talk about the model of perfect competition, or we talk about monopoly, what we always do is there we've got a picture that involves some cost curves. So there's some curves that have to do with cost and some curves that have to do with revenue. And we're looking for where marginal revenue equals marginal cost. And we identify that by the intersection of two curves, and we put a dot there, and we put Q star or QM and P star. And it feels very deterministic. It feels like, okay, that's what's going to happen. Well, what we know is theoretically, that's what would happen if a firm is maximizing its profit, so if that firm is run by a manager who's making good decisions, then that's the quantity that they would most likely produce and the price that they would most likely charge. And it feels like there's no uncertainty, like that's always what's going to happen. Here, when we're talking about oligopoly, we've got firms that have to make predictions about what the other firm or firms are going to be doing, and there's not really, it feels less deterministic. So what we're going to be thinking about here is, so what's the likely outcome? Okay, and so let's think about how you would start to solve this game. And anytime you're looking at a game, the first thing that you need to start looking for is what we refer to as a dominant strategy. And a dominant strategy is simply a strategy that is always the best strategy for you to play, regardless of what the other player is doing. And so let's think about player A here. In this case, player A has a dominant strategy of playing up. So up is a dominant strategy for A. Let's think about how you would figure that out. So let's suppose that B chooses to play the left strategy. So if B chooses left, then let's think about what it would be best for A to do. Now, this is not how the game works. A is not seeing what B does and then choosing a strategy. They're choosing simultaneously. But A would be able to reason through this in this manner. If B chooses left, then A is either going to get 10 or negative 10. So if B were to choose left, then A's best strategy is to choose up. So from A's perspective, they should choose up. Okay? But B might not choose left. If B were to choose right, then let's think about what it would be best for A to do. So if B were to choose right, now we're in this column, and A is either going to get 15 or 10, and would rather have 15. So if B chooses the right strategy, then the best strategy for A to have chosen would be up. And so now you can see why we would call this a dominant strategy for A. A's best strategy is always to choose up. Now let's think about, I'm going to draw a line here. Let's think about what this would look like if we took the perspective of B. Okay, so if we are now player B, now we're going to reverse this and say, okay, well, A could either choose up or down. Okay, so if A now were to choose up, so now we're in this row, and since we're B, we're either going to get 20 or 8. We'd rather have the 20. So if A chooses up, then it's best for us to have chosen left, right? So B, our best strategy would be left. Well, A might not choose up, A might choose down. So if A chooses down, then in that case, we're either going to get 7 or 10. We'd rather have the 10. So if A chooses down, if we're in this row, then our best strategy is right. And you can see that B does not have a dominant strategy. B's best thing to have done depends on what A did. So now we've got to say, okay, well, so what would be the likely outcome? How would we solve this game? One possibility, and probably the most reasonable possibility, is to recognize that A has a dominant strategy and will likely play it. So one possibility, and again, I will say that in my opinion, this is the likely outcome, is that A plays its dominant strategy. Well, if A is going to play its dominant strategy, which is up, then the best thing for B to do is to play left. B plays left. Because if B believes that A is going to play its dominant strategy, then it needs to play left. So if A plays its dominant strategy, and let's put that here up, and B plays left, we're going to be in this outcome. Okay, so that would be a reasonable way to think through this problem. The likely outcome is probably this one right up here. There's some other possibilities, and let's talk about one of those. There's something that is sometimes referred to as a secure strategy. And so what we could do is we could say, okay, well, maybe A won't play their dominant strategy. It's not a guarantee. I would argue that it's going to be challenging unless you come up with something that's not captured in this table to convince me that A is not going to play their dominant strategy, because it is obviously the best thing for them to do no matter what. But let's suppose you're just not sure and you want to play it safe. Let's suppose that B is very risk averse. They don't like the idea of any risk. Then they could play this secure strategy, and that is that what they may do is they may choose the strategy with the highest low payoff. So choose the strategy with the highest low payoff. Some textbooks call this the max-amend strategy. So here's how this would work. If A chooses up, then the worst thing that could happen to B is that they get 8, right? That's their worst outcome there. If B were to choose down, then the worst outcome, or if A were to choose down, then the worst outcome for B is either going to be 7 or 10. The worst outcome is 7. So if they're going to choose the highest of the low payoffs, then they might choose this right strategy, because the worst outcome is higher with the right strategy than it would be with the left strategy. Okay? So you can see this way as well. The worst strategy, the worst payoff is 7. Here the worst payoff is 8. So you go with the strategy that gets you the least bad outcome. I don't find that to be very convincing. And in fact, I think the evidence indicates that this isn't done very often. Again, unless the person running firm B was extremely risk averse. Let's talk about the Nash equilibrium. So I'm going to go back and circle our likely outcome right there. And let's think about what's known as a Nash equilibrium. So a Nash equilibrium, I'm going to scratch person A out here and move it over there so it doesn't get in the way. So a Nash equilibrium is a situation where once the outcome is determined, nobody regrets their strategy. So this is a situation where no player regrets their strategy. We've got to add one thing to that. I'm going to say, given what the other players did. Given what the other players, or in this case, player did. So let's think about why this outcome fits this definition. So if we're in this outcome, that means that B chose left and A chose up. Does either player regret the choice that they made? So let's think about B. So player A chose up. That means that we're in this row. Does B regret choosing left? And the answer is no. They don't wish that they had chose right, because then they would have 8 instead of 20. So B doesn't regret the strategy. Now let's think about it from A's perspective. A sees that B chose left. Does A regret choosing up? Does it wish that it had chosen down? And the answer is no, because if it had chosen down, it would have gotten -10 instead of +10. So neither player regrets their strategy. Let's think about one of the other outcomes. So let's think about this outcome right here, where both of them get 10. A chose down and B chose right. Let's start with B. So B observes that A chose down. Does B regret their strategy? So A chose down. We're going to be in this row right here. And B does not regret their strategy. They don't wish that they had chosen left, because then they would have 7 instead of 10. So B doesn't regret their strategy, but let's think about A. So now A observes that B has chosen the right strategy. That means that A was either going to get 10 or 15. They ended up with the 10. Do they regret their strategy? Yes, they do. They regret that they didn't choose up, because then they would have had 15 instead of 10. So B doesn't regret their strategy, but A certainly does. So that can't be a Nash equilibrium, because at least one of the players regrets their strategy. And if you go through that, you'll see that these are not Nash equilibria either. So the Nash equilibrium is something that we'll identify in other types of games. And what we'll see is that there are some games where there is no Nash equilibrium. Some games have multiple Nash equilibrium. And we'll also see that the Nash equilibrium is not necessarily the best outcome for the players that are involved in it. Okay? Let's think about another game. And we'll think in this game about what we would say a pricing decision game. So let's think about a game where the firms have to decide on pricing. So pricing decision game. Anytime you've got a situation where there's a small number of firms, what we're going to see is that there's going to be an incentive for those firms to collude, to secretly cooperate with each other. If you've got lots of firms, then it's impossible for the firms to collude. We'll talk about that why a little bit later. Let's not say impossible. It's nearly impossible for the firms to collude. To try to get 1,000 people to all agree to do one thing and then stick to that and actually do it is way harder than it is to try to get 2 other people to agree to something and stick to it. So the smaller the number of firms or people involved, the easier it is to collude. So in an oligopoly with a small number of firms, that's when you tend to observe collusion. So let's think about a situation where we've got 2 firms and each firm has to decide whether to charge a high price or a low price. And so let's put together our game matrix here. And I'm going to put same setup. Each firm's going to have 2 strategies. We'll put firm B up here, and again, we'll put firm A here. And our 2 strategies this time are either to charge a low price or a high price. So B is going to have the choice between a low price and a high price, and A also is low price, high price. Let's think about the payoffs, and let's suppose that if the 2 firms each charge a high price, if A charges a high price and B does as well, then we're down in this cell down here in the bottom right-hand corner. Let's suppose they each earn 10, and this could be 10 million in profit for a year. We could make this in terms of a month. We don't need to worry about that. The absolute magnitude of these numbers is not what's important. On the other hand, let's suppose that each of them charges a low price. Well, if each of them charges a low price, then let's suppose they don't make any profit. Now, let's talk about those 2 outcomes. Obviously, from the point of view of the 2 firms, this is the best place to be, right? Where each of them charges a high price. And we're assuming here that the customers can only buy from either firm A or B, okay? So if those 2 firms can get together and agree to charge a high price, then they can make profit On the other hand, if they don't agree and they each charge a low price, they're not going to make anything. Okay, so from the point of view of the firms, this is clearly a better outcome than that is. But now let's think about these two off-diagonal cells here, where one firm charges a high price and the other firm charges a low price. If one firm's charging a high price while the other firm charges a low price, customers are going to tend to buy from the firm with the low price. And the firm with the high price is going to not be in a good spot. Let's suppose the firm with the high price, in this case firm B, loses 10, and firm A stole all the customers and makes 50. Or we could think about this outcome where firm A charges the high price and firm B undercuts their price, charges a low price. And in that case, firm B, the firm with the low price, is going to make 50, and the firm with the high price, firm A, is going to lose 10. So this is a very different game from that one. From the point of the view of the two firms, again, this is the best outcome. But now let's think about what the likely outcome for this, for the two firms is. Let's go through what we did over here. Okay, so let's take the point of view of firm A first. So let's think about what firm B could do. So if B chooses low, so we're firm A. If B chooses low, then we're in this column. And that means we're either going to get 0 or negative 10, and we'd rather have 0. So if B is going to choose low, we need to also choose low. A chooses low. Or it could be that B chooses high. If B were to choose high, then let's think about what it would be best for us to have chosen. If B chooses high, then we're either going to get 50 or 10. And we'd rather have the 50. So if B is going to choose a high price, it's best if we have a low price. And you can see that for firm A, choosing the low price is a dominant strategy. Let's do the same thing, but now let's take firm B's perspective and let's consider the two things that A might do. Well, A could choose low. If A chooses low, now we're taking the perspective of B, so that means if A chooses low, we're in this row, and we're either going to get 0 or lose 10. We'd rather get 0. So that means if A is going to choose low, B's best place to be is also to have chosen low. But of course, A may choose high. If A chooses high, then B, so now we're in this row, and us as B, we're either going to get 50 or 10. We'd rather have the 50. So if we know A, we're going to choose high, we'd rather choose low and steal market share. You can see that dominant strategy for each firm is to choose low. The likely outcome for this game is right there. Even though there's a better place for the two firms to be, from the point of view of the two firms, this is clearly a better outcome than that is. And yet, the way these incentives are set up, each firm has a dominant strategy to choose low. Now, from the point of view of consumers, this is a good thing, right? It is hard for firms to collude secretly. And we'll talk about that, but the likely outcome, our Nash equilibrium, the Nash equilibrium for this game is each chooses low. Let's say chooses a low price. This is an example of what we call the prisoner's dilemma. Okay, you may have seen this. It's the most basic, one of the most basic games in game theory, and a lot of times it's introduced as the prisoner's dilemma. And the idea behind the prisoner's dilemma is this. You have two criminals that get caught engaged in a illegal activity and it's a relatively minor crime, but they get caught red-handed in that minor crime, so the police could lock them up for, say, a year right now. But the police suspect that they have been engaged in a major crime and they want the criminals to confess. Now, everybody knows that confessing is not the thing that you should do if you want to be a successful criminal, right? The unwritten rule of doing anything wrong is deny everything and stick to your story. The problem is that the police can put the prisoners into a dilemma by offering them this deal. Right now, we could lock you up for a year, but if you confess and implicate your partner, we'll let you go free and your partner will spend 20 years in prison. And they offer both of them that. In other words, what they do is they pit the incentive to look out for your individual best interest against the incentive to look out for the best interest of the team. And that's what's going on here. What you start to realize when you think about things enough is that it's often the case that what's in your own individual best interest is not in the best interest of the group or the team. This is easy to see when you look at a sports contest. If you've ever played sports, especially a sport like basketball or football or baseball, a team sport, not an individual sport, but a team sport, then you probably will easily realize that there are lots of times when what's in the best interest of one individual player on the team is not necessarily in the best interest of the team as a whole. In other words, being a good coach means that what you need to be able to do is you need to be able to get players to give up their own individual performance for the performance of the team. Sometimes you have to not go after good stats if you want the team to win. This is easy to see on a basketball court, right? You get one player that's just trying to score as many points as they can and they just take too many shots and they don't pass when they should and they're not running plays the right way. You've probably played with a player like that. And the team suffers because that player is being selfish. Now, what's happening there is you've got conflicting incentives, and that happens all over the place when we're talking about sports, but also when we're talking about family interactions and when you're talking about the dynamics between being a worker and the success of the business. It crops up all over the place when you start thinking about how to manage employees. And this is just an example of that in the case of two firms. What's in the best interest of the two firms together is to collude. But what's in the best interest of each individual firm by themselves is to choose their dominant strategy. Does that mean that we would always observe the two firms failing to collude? And the answer is no. We'll talk about when firms might. Let's start by talking about why is collusion unlikely? So we understand the incentive to collude. They would like to go after these profits. They end up, if they play their dominant strategy, in a place where they earn no profit. And again, we would think about this as economic profit. We've talked about that in previous videos. So why is collusion unlikely if we're talking about firms? Well, first off, it's illegal. It is illegal for firms to collude. This is specifically prohibited by the Sherman Antitrust Act of 1890 and the other pieces of antitrust legislation that have come along since 1890. Just because something's illegal doesn't mean that it's going to prevent every firm from doing it. So there are lots of cases where firms have tried to collude and sometimes done it successfully. But that's the first deterrent. It's illegal, and so we don't see as much collusion as we would if it was not illegal. So that's the first thing. And then the second thing is a low price is a dominant strategy. And that is probably the largest piece of information in terms of why collusion is unlikely. Because firms have an individual incentive to choose that low price to try to undercut the other firms. This pricing decision game, you can apply this to a lot of other types of games between firms. So you can think about this as advertising. So we tend to see a lot of advertising in oligopoly markets. And it turns out that the advertising is this unusual kind of advertising that firms don't want to do. This happens with soft drinks. It happens with cigarette manufacturers. It happens with cereal manufacturers. Let's think about cigarettes, because that's an interesting one. If you've got two firms, and if you're interested in more about that, you can go to a Principles of Micro video of mine that is on Oligopoly, where I go through some other examples of the prisoner's dilemma, and I do the prisoner's dilemma in a little bit more depth. So if there was something you didn't understand, it might be good to go to that. But if you think about maybe a situation where you had two cigarette manufacturers, and usually I use Marlboro and Camel, those two manufacturers do not want to advertise. And the reason they don't want to advertise is because advertising doesn't create new smokers. People don't start smoking because they saw an ad. There are other reasons why people start smoking, because family members smoke, or they start hanging out with friends who smoke. There are a variety of other things, but it's not because you were a non-smoker and you just saw an advertisement one day. So the firms don't want to advertise. In fact, it's a waste of their money. But advertising is a dominant strategy. If both firms advertise, smokers don't switch. If no firm advertises, smokers tend not to switch. But if one firm advertises and the other firm doesn't, then people who are already smokers tend to switch to the firm that's advertising. Advertising is a dominant strategy. So the best outcome for the two firms in that game would be don't advertise. Don't waste the money on the advertising, and you end up with some profit. But by advertising, because it's a dominant strategy, they end up wasting some of the profits that they could make. So that's an example where you can apply a prisoner's dilemma game to a different type of decision. You can also think about the decision to make a high-quality product versus a low-quality product. And you'll see that oftentimes for firms, making a low-quality product is a dominant strategy. Firms a lot of times are accused of just making products that will break just so that we as customers have to repeatedly buy it. They don't want to do that. That's not their goal, but because making a cheaper product is a dominant strategy, they get pushed in that direction. So there are lots of other ways that you can apply this prisoner's dilemma game. And it's not just firms. Nuclear proliferation, you can use this prisoner's dilemma game to understand why countries tend to arm themselves. You can use it in a whole bunch of really dirty campaigning. To campaign dirty is a dominant strategy. So let's think about a different type of game. And now we're going to think about a situation where firms are better off cooperating with each other. And it doesn't necessarily have this bad connotation that this type of cooperation does. This type of cooperation, if the firms can collude and charge a high price, this is bad for customers. I'm going to erase this and we'll talk about firms having an incentive to coordinate their decisions. In the previous game that we looked at, the prisoner's dilemma, the benefit to a firm comes at the expense of the other firm. But that's not always the case. Sometimes the benefit to one firm also results in a benefit to the other firm. So let's look at a game like that. Let's suppose that we have two firms and they each have two strategies. Maybe these firms are producing a product and they have to make a decision about the type of electricity, whether it's, say, 90 volts or 120 volts that their appliance is going to run on. or maybe the appliance has outlets on it, and so they have to decide the type of the voltage for the outlet. Okay, so let's suppose that we put our game together here, and we've got same thing as usual, firm A, firm B, and the two strategies are that they can choose to have 120 volt outlets or 90 volt. And both of them have the same choice, the same two strategies. And let's think about the payoffs here. So let's suppose that if both of them make a product that runs on 90 volt outlets, then let's suppose they each get 100 in profit. Or if they both make appliances that run off 120 volt outlets, then they also get 100 each. But if one of them makes an appliance that runs off 120 volt outlets or has 120 volt outlets on it, while the other one creates a product that uses 90 volts, then they've got a problem. Let's suppose they make nothing in those cases. So in this case, it's best if the firms choose the same. That way customers can use the appliances together. Okay? And it doesn't matter to them if they're running off 120 volts or 90 volts. What matters is that the appliances can work together. Okay? So this is a situation where the firms are made better off if the other firm does the same thing, or there are outcomes here where coordinating the decision is the best thing to do. And it's best not just for the firms, but it's best for customers as well. So you can see if you go through, I'm not going to do it, but if you go through, you'll see there's no dominant strategy in this case. Your best outcome always depends on what the other firm does. And so when you think about the two options the other firm should do, you're always best choosing the same option. So there's no dominant strategy. Let's think about what would happen. How would we essentially work out this game, work through this game, if the firms cannot talk to each other? If the firms can talk to each other, it's no problem, right? If you're a firm and I'm a firm, then I would come to you and I'd say, look, you're making a product, I'm making a product, we need to coordinate here. Let's just decide right now if we're going to have things go on 120 volts or 90 volts, and I don't care which one it is. Just choose one and I'll do the same thing. That makes it easy. But there are lots of times when the firms can't do that. So if the firms can't do it, then one way that, say, we could solve this is the government can set a standard. And this is typically done, especially in the case of voltage that, say, runs to households, and you can have, say, 220 that big appliances run off of, but usually 110 is what we run regular appliances off of. And so the government does tend to set standards in these cases, and that can help coordinate the decision. And it's also the case that once the firms have reached an outcome here, there's no incentive to cheat, right? So the firms have no incentive to break the agreement. In fact, that would make them worse off. And I'll leave it to you to verify this, there are two Nash equilibriums. This is a Nash equilibrium, and that's a Nash equilibrium. In other words, if the two firms were in this outcome, neither of them would wish that they had chose 90 instead of 120. Or if both of them have chosen 90 and we're at this outcome, neither of them wishes they would have chosen 120. So these are both Nash equilibrium. So it's a very different type of game that leads to coordinating behavior between firms that's good for everybody involved. We can also think about another type of application of this game theory type setup to monitoring employees. So if I were thinking about monitoring, and here what we're thinking is monitoring to make sure that your employees are working. Anytime you've got a manager and you've got employees, the incentives for the manager and the incentives for the employees conflict with each other. And so let's think about a game like this. Let's suppose we have, let's put our workers up here. So I'm just going to say worker. And that worker has two strategies. The worker can either work or they can shirk. Not work. Sit around and look at their phone. And we've looked at this type of situation before in another video. And our manager can either choose to monitor the employees or not monitor. So you can monitor or don't monitor. And let's think about a simple setup for some payoffs here. Let's suppose, well, I'm just going to go ahead and put the payoffs in, and then we'll talk about them. -1 and 1, 1, -1, 1, -1, -1, 1. So let's just talk about, let's suppose that the manager chooses to monitor. Well, if the manager's monitoring, then the best outcome for the worker is to be working. If the manager's monitoring and you get caught shirking, well, then you're in trouble. You lose one. If the manager is not going to monitor, then the best outcome for the worker is to shirk. If you know the manager's not going to be in today, well, heck, you don't have to work. Just look at your phone all day. Or if the worker is working, then we're in this column, and the best outcome from the manager's point of view is not to monitor. If the workers are working, then save the monitoring effort. You're better off because they were working anyway. On the other hand, if the workers are shirking, then your best outcome from the manager's perspective is to monitor them and keep them from shirking. So this would be a situation where there's no dominant strategy. There is also no Nash equilibrium to that game. If you evaluate each of the 4 possible outcomes, you'll see that none of them could be a Nash equilibrium. It's also the case that each player would like to keep their strategy secret, right? If you don't keep your strategy secret, then you're going to get caught, right? Or you're always going to get fooled. If they know that you're always not going to monitor, well, then you got a problem. You're not going to catch them shirking. And there's going to be a lot of shirking. The way that a player would want to play this is to randomize their strategy. We call it a mixed strategy. So here, the mixed strategy is the best. And that is a strategy where you randomize. You don't always shirk. You don't always work. You essentially randomize. You shirk at random times. And as a manager, what you need to do is you need to randomly monitor, and it's got to be truly random. So you would think about just flipping a coin. You either monitor that day or you don't monitor, but you certainly don't be predictable. Okay. Let's talk about another application of game theory, and that would be something that we call Nash bargaining. Nash bargaining. So let's suppose the setup for this game is that we've got a labor union and we've got management, and they're bargaining with each other about how much of a $100 surplus should go to the union and how much should go to management. So they've got to split this $100. We could make it a much bigger, more realistic dollar amount, but there's no reason to do that. And let's suppose, to keep it simple, that the $100 can only be split in $50 increments. So this is a little bit more complicated of a game. Now there are going to be 3 strategies. And each of the two players, the union and management, we'll put the union up here. The union can either try to get 0, 50, or 100. And management has the same two strategies, 0, 50, or 3 strategies, or 100. So this is management over here. And let's suppose that the game works this way. They only have one shot at an agreement. And what they're each going to do is they're going to write a dollar amount on a piece of paper. They're going to fold it up and they're going to drop it in the middle of the table. That piece of paper is either going to have a 0, a 50, or a 100. And then the arbitrator is going to look at the two pieces of paper. And if the amounts add up to less than 100, then they each get what they wrote on the paper. So if you wrote 50 on the paper and the sum of the $2 amounts adds up to less than 100, you get 50. Or if you wrote 100 and the other person wrote 0, you get the 100 and they get the 0. On the other hand, if the $2 amounts add up to more than 100, you each lose $1. Okay? And so let's put the payoffs here. So I'm going to divide each of these cells in half. And it's relatively easy to figure out the two payoffs. If they each wrote 0, then 0 plus 0 is less than 100 and they each get 0. If they each wrote 50, well, 50 and 50 add up to 100, and that means that they each get what they wrote on the paper, which is 50 and 50. If they each wrote 100, well, that adds up to more than 100, so they each lose 1. On the other hand, let's suppose management wrote 0 and the union wrote 50. Then the union's going to get the 50 and the management's going to get 0. Down here, if management wrote 50 and the union wrote 0, then the union's going to get 0 and management gets 50. Or right out here, if management wrote 0 and the union wrote 100, then the union's going to get the 100 and the management gets 0. Down here, management wrote 100 and union wrote 0, so the management is going to get 100 and the union gets 0. And then here, this outcome is where the union wrote 50 and management wrote 100. That adds up to 150. They each lose 1. Same here. They each lose 1. There's what the payoffs to that game look like. There are 3 Nash equilibria to this game. I'll circle them. This is a Nash equilibrium. This is a Nash equilibrium, and that is a Nash equilibrium. I'll leave it to you to verify that if we were any of these 3 outcomes, neither side would regret their choice. It's not necessarily a good outcome for one side or the other. I'm not saying that they would be happy with the outcome. I'm just saying they wouldn't be better off if they had chosen a different strategy. The outcome for this type of game is hard to predict. If we look at this type of game, and researchers have done experiments, put people into situations where they're playing a game like this, and this outcome where they each tend to split it, that's an outcome that we tend to see quite a bit in this type of game. So in real-world experiments, people are often drawn to this central outcome where they split the amount. That doesn't necessarily mean every time this game of this type was played that would be the outcome. But it does happen more than just what you would expect from random chance. Let's think now about multiple plays of games. So let's start by thinking about what we're going to call infinitely repeated games. So infinitely repeated games. Let's think about present value. We need to kind of review that, because if we've got an infinitely repeated game, then clearly what's the thing that's going to be important here is the present value of the stream of payments that you would get from this infinite game. And remember that if we were thinking about the present value of a stream of payments. Let's suppose you get a payment right now. So a profit amount in time period 0, that's right now. And then you get another one after time period 1, then we have to discount that by 1 plus I. And then you get another payment at the end of time period 2. We'll call that profit at time period 2. And you've got to discount that, I, and now we've got the squared term, and then that continues just indefinitely. Well, we talked about something similar to that. If you write the present value, here's what the present value looks like. The present value is equal to 1 plus I over I multiplied by the profit amount. We will assume that these profit amounts are the same in every time period to make it simple. We've seen something like that before. Actually, in an earlier video, we saw something that said the profit value or the present value is equal to pi divided by I. And you might look at this and say, well, where did that little thing up there come from? Well, in that thing that we did earlier, we were assuming that the first payment was at the end of the first year. That one didn't include this payment, this immediate payment. If you include an immediate payment in time period 0, then it changes this term by a little bit. So if you're thinking about that and you say, well, that's not what it looked like earlier, that's the difference. If we ignored that, if we said that, okay, you don't get that time period 0 payment, all you get is after a year and then after 2 years, then this term up here, this I would be a 0 right there, and it'd just be 1 over I times profit, which is profit over I. So don't let that bother you. It's a minor difference. So now that we've kind of gone back over that, let's talk about something known as a trigger strategy. So trigger strategy. So let's suppose that we've got a simultaneous move game, and it's that pricing game or a pricing game like what we saw with the prisoner's dilemma. So let's suppose we have, let's look at the game again. Suppose we've got firm A over here and firm B here, and they can either choose a low price or a high price. Same for firm A, low price or high price. And we've got some outcomes. Let's suppose that if they both choose the high price, they each get 10. If they both choose the low price, they each get 0 profit. If one chooses a high price and the other chooses a low price, then the firm that chooses the low price is going to get all the profit, and the firm that chooses the high price is going to lose some money. Let's suppose 50, and we'll make this a negative 40. And then same here, negative 40 and 50. So that's an example of a pricing game. Likely outcome is right here. Each of them have a dominant strategy to choose the low price. That's in a one-shot game. Let's suppose this game is repeated over time. Then the firms might be able to preserve a collusive agreement by adopting what's known as a trigger strategy. So let's suppose the firms get together. Suppose you're a firm and I'm a firm. Now keep in mind this is illegal. If you're a firm and I'm a firm and we get together and we have a talk about colluding and the government finds out, we're in trouble. But let's ignore that minor complication for right now so that we can think through a trigger strategy. Let's suppose we get together. We have a meeting and we say, okay, look, here, let me explain what's going to happen. So we're going to play this game now and we're going to play it in the next time period and the next time period, and that's going to go on infinitely. And as long as we will collude, as long as you charge the high price, I will also charge the high price, and we will enjoy this stream of $10 profits indefinitely. And we can calculate the present value of that stream of profits. On the other hand, if you ever choose the low price and break our agreement, if you ever choose that low price, then I will choose the low price from then on. If you ever betray me and undercut me, then what you're going to get is you're going to get that $50 payment one time, but from then on you're going to get zero. And I'm going to get burned once. I'm going to lose the 40. But then from then on, you're getting zero. And the same goes for me. If I ever break the agreement, you get to, then the trigger gets pulled, and then you don't cooperate from then on with me. And so if I break the agreement, I'm going to get zero from then on. So let's think about when they would be more likely to abide by the collusive agreement than they would be to go ahead and go after that one-time payment of $50. So if the present value of the stream of $10 payments is bigger than that $50 instant payment, colluding is the best strategy. So they collude. I'm going to say they continue to collude if the present value of that stream of $10 payments, that's not just one $10 payment, that's the infinite stream, if that present value is bigger than the $50 that they would get one time. Now let's write out what that present value is, and we can use this right here. So if that 1 plus I divided by I multiplied by 10, because 10 is the profit amount, if that is greater than 50, then they are better off colluding. And if you do a little bit of algebra, multiply both sides by the I and then solve for I, what you get is that colluding is the best strategy if that discount rate is less than 1/4. In other words, if the discount rate is less than 25%, then they are better off colluding and not breaking the agreement. And so a trigger strategy will work in that case if the discount rate is less than 1/4. So that can be a way that firms might have a higher probability of colluding if it's an infinitely repeated game. If it's a one-shot game and there's no tomorrow, there's no possible way to implement a trigger strategy, right? If it's a one-shot game and you come to me and you say, okay, well, look, here's what the game looks like. I want you to choose that high price. Well, if I believe that you're actually going to choose the high price, I'm better off choosing the low price because I win the game. I get the 50, there's no tomorrow, and you lost. You were stupid by charging the high price, right? And if you did that to me, and I actually charged the high price, you would be able to say, well, that was a stupid move on your part. So let's think about, I mentioned even in a one-shot game earlier that it's not the case that we always observe the firms not colluding. Sometimes the firms do actually collude even in a one-shot game. And so let's talk about conditions under which collusion is more likely in a game of this type. I mentioned one of them. Let's put let's list them right here. A small number of players. Small number of players. Collusion is more likely if you have a small number of players. If there are lots of players, for example, let's go to the basic prisoner's dilemma. If it's not just that you have a single partner in crime, if there's 10 of you, then all it takes is one of them to confess and the whole agreement breaks down. So it's easier to get a small number of people to cooperate than it is a big number of people. So the smaller the number of players, the higher the likelihood that they'll be able to collude. Still probably not very likely, but certainly with a large number of players, you hardly ever see collusion. It could be another thing that affects whether or not they collude is firm size. So if you've got economies of scale in monitoring, right? So if If it's easier to monitor the bigger the scale of the operation, then it's often cheaper for a larger firm to monitor a small firm than it is the other way around. And so the size of the firms can affect whether or not each firm is able to monitor whether or not the other firms are breaking an agreement. This is important when you start to think about a large cartel like, say, OPEC, the Organization of Petroleum Exporting Countries. OPEC is made up of some small countries and some big countries. And so the size of those countries can affect their ability to monitor whether or not the other countries are breaking the agreement. You can also think about the history of the market. So if this is a multiple period game and the players have a history of cooperating, that history of cooperating would lead you to believe that they will be able to continue to cooperate in the future because they have experienced the benefits of cooperating and they understand it. So having a multiple period game, especially if there's a history of colluding between the firms, increases the chance that there will be collusion in the future. And then punishment. This is number 4. So if the firms can punish each other for breaking the agreement, that's the idea behind a trigger strategy. If there's punishment, then that increases the probability of cooperating. And this is true even in a one-shot game. If you've got 2 criminals and one criminal is given the opportunity to go free if they confess and implicate their partner, but if they implicate their partner, if they fear that their partner will seek retribution, like get somebody else to harm them, they might say, you know what, I'm not going to break that agreement. I'm going to keep my mouth shut. So you can see that there are a number of things that can increase the probability of the firms actually being able to reach this. A trigger strategy is just one of those things. Let's think about finitely repeated games. So let's suppose that there's an end to the game, but it's uncertain. So let's suppose that there's an uncertain... Actually, I'm going to clear this off and then we'll talk about that. All right, let's think about a finitely repeated game. So this is a game that has a definite endpoint, but let's suppose it's uncertain. So there's a probability now, and we'll think about that probability of being theta. It's a Greek theta. So if we think about the probability that the game will end. So this is the probability the game will end after each time period. So now in this case, nobody knows when it's going to end. There's some probability. It could be 5% chance that it's going to end. It could be an 80% chance that it's going to end. That's we're going to let be represented by theta. In this situation, the game is exactly like an infinitely repeated game. So let's suppose, for simplicity, let's make our discount rate 0. That just makes it easy to figure out the present value stuff. And let's suppose that each firm adopts a trigger strategy. So each firm's going to adopt that trigger strategy we just talked about. If a firm cheats, it earns 50 now. So if you cheat, you get $50 now. If it cooperates, it earns $10 now. So cooperate, you earn $10 now. Say 50 one time. And then if you cooperate, you get the $10 now, plus you get a 1 minus theta probability of $10 in the next period. And then if we think about the time period after that, now the probability that it's going to last 2 time periods, you'd multiply the probability that it's going to continue times the probability that it continues. That would be a 1 minus theta squared probability of earning $10 in 2 periods. So if you're thinking about flipping a coin and the probability of a head is 50%, then the probability that you will flip 2 heads in a row, you have to multiply that 0.5 times 0.5. There's a 0.25 probability. So you're multiplying those probabilities. These are independent events, so that's why you have the probability times the probability again. That's where the squared comes in. And we would say et cetera. If we're thinking about the probability of it going 3 periods, it would be 1 minus, that should be a theta, not a q. 1 minus theta cubed. That means the profit, if you cooperate, the profit from cooperating, I'm going to put a little c down there, would be equal to the $10 now, plus the 1 minus theta times that's theta times 10 after 1 period, plus the 1 minus theta squared times 10 plus. So you can see that that's something very similar to a present value calculation, right? And there is no, this simplifies to 10 over 1 minus theta. So there's no incentive to cheat if the profit that you're going to earn by cooperating is bigger than that one-time payment. So if the 10 divided by 1 minus theta is greater than what you get, or greater than or equal to what you get from the cheating and getting a $50 payment one time, then you would continue to collude. And if you solve that for theta, you see that if theta is less than or equal to 4/5, then there's no incentive to cheat. So adapting this to a finite game with an uncertain end, that's relatively easy, especially if you simplify by not having to worry about the discounting. Let's talk about a repeated game with a known final period. Repeated game with a known final period. So let's suppose it's a 10-period game. So we know the 10th period is the last period. Well, let's think about the incentive to collude in that last period. Let's go to the 10th period. In the 10th period, there's no tomorrow. So a trigger strategy won't work because there's no tomorrow. There's no future payments that you could possibly earn. So the incentive to cooperate in the last period is practically zero because there's no tomorrow. Well, if you're not going to cooperate in the last period, now let's go to the period right before that. If you're not going to cooperate in the last period, there's no incentive to cooperate in the 9th period. And you can see that if there's no incentive to cooperate in the 9th period, there would certainly be no incentive to cooperate in the 8th period. So the whole thing unravels. If you know the end, and the end is set, and it's known to everybody in the game, then that turns out to be the same outcome as just a one-shot game. Okay, so knowing the final period destroys the incentive to cheat, not just in that last period, but also every period prior to that. So collusion is not going to work in a game that has an end period that's known. We call this, not surprisingly, the end of period problem. End of period problem. There are some important applications to that. So let's suppose that you have a worker and that worker announces that they're going to quit on a particular day. Right? So the worker, I don't know, maybe it's a 2-week notice. Well, so now the worker knows that their final day is that 2-week, 14 days from now is their last day. Then on that last day, their incentive not to shirk is greatly diminished. It's their last day. There's no tomorrow, right? So why work hard on the last day? Well, if you're not going to work hard on the last day, your incentive to work hard on the day before that is diminished as well. And so this end of period problem can arise if you have a worker that submits a 2-week notice, right? Or if there is some final day of work for that worker. Maybe it's employees that are just working for the summer. Maybe they're not, they haven't quit to take another job. Maybe it's just their summer vacation job and the end of summer is coming. That's an end of period problem. And what you tend to see is that it unravels from the end and they start shirking way earlier. There's a couple ways as a manager, I guess, you could handle that. And that is you could immediately fire them when they give their 2-week notice. Then you don't have to put up with a worker who's shirking for the last 2 weeks. So as soon as they announce they're quitting, fire them. Probably not a good strategy, because if you got a reputation for doing that, then a worker would never give you the 2-week notice, right? So I would certainly not recommend that as a strategy, but if all you were wanting to do is fix that end of period problem, that would be a way to do it. A better strategy would be to extend the game. So let's suppose that you've got a worker that submits their 2-week notice and you know there's an end of period problem. So now what you could do is remind the worker that you can be a good resource in their future jobs. You could say, you know what, I'll be happy to be a reference for you in the future, not just for a job right now, but maybe a couple of years down the road. And by reminding them that this is a game with more periods than just this 2 weeks, then you might be able to give them an incentive to go ahead and work hard, and even up until that very last day, because they know they can use you as a resource. Or you could make sure that your employees know that you are well connected to other employers in the area. That way, if they demonstrate to you that they are shirking, you could let other employers know that. So that would be a way of kind of extending the game beyond that last period. Let's talk now about what we would call multi-stage games. And these are a little more interesting in my opinion. What we'll do now is we'll think about a game that where one player acts first and then the next player responds to what that first player did. So we call these multi-stage games. Multi-stage, there's probably a hyphen in there, multi-stage games. So our players are going to make sequential moves, and when we start thinking about a multi-stage game, what we do is we think about what's called the extensive form of a game. Not the normal form that we were already working with, but the extensive form. And this builds time into the game, and it actually builds information into the game. What we do is we use what are referred to as decision nodes. So at each node, somebody's going to be making a decision. Okay, so let's suppose we had a game that looks like this. We're going to have player A, and this is going to be a node here. And at that node, player A is going to decide either up or down. And then once player A has made that decision, then that leads us to a new node where player B is going to make a decision. Okay, so here would be player B making a decision if player A chose up. Down here is where player B makes a decision if player A chose down. And let's suppose that B has those two strategies of up or down. And then we get the payoffs. Now in this case we don't have a cell. What we're going to do is we're going to write the payoffs. I'm going to write one number and then a comma and another number. And the first number will be the payoff to A, and the second number will be the payoff to B. Down here, B gets to either choose also up or down. And so we're going to have payoffs at each of these 4 possible outcomes. Let's suppose if player A chooses up and then player B chooses up, A gets 10 and B gets 15. If A chooses up and then B chooses down, then A is going to get 5 and B gets 5. If B chooses down and player A chooses up, they each get 0. And if A chooses down and B chooses down, then A is going to get 6 and B is going to get 20. So this is a sequential game. Player A moves first, player B moves second. And clearly, player B's strategy depends on what player A does. And the nice thing for player B is they get to react to what player A does. Player A is the first mover. Okay. So let's think about if A were to choose up, then now B is right here at this node and they get to choose up or down, which means they're either going to get 15 or 5. So if A were to choose up, the best outcome for B is to also choose up. So that's how we would analyze this type of sequential multi-stage game. Let's consider the outcome where A chooses down. A chooses down, and then B chooses down no matter what A does. Okay. So let's suppose B says, look, I don't care what you do, I'm choosing down. And so let's consider this outcome. A chooses down, B chooses down. And if you look at this outcome, what you start to realize is that neither of them would regret their strategy. In other words, this is a Nash equilibrium. This outcome, where B has said, I'm going to choose down no matter what, and A chooses down, that's a Nash equilibrium. Neither of them would regret their strategy, but is it a reasonable Nash equilibrium? So in other words, would B choose down if A chose up? So B has said, I'm choosing down no matter what. Well, let's suppose A chose up. And you can see that if A chooses down, then choosing down for B is an easy decision because they're choosing between 20 or 0. Okay, well that's fine. What if A chose up? Would B still choose down? Well, if A chose up and B chooses down, then they're going to get 5 instead of 15. And so the idea that B would choose down no matter what is a little bit far-fetched to begin with, right? It's what we would describe as not subgame perfect. In this subgame right here, if we treated this as just a game where B has to make a decision, then B is better off choosing up. Okay, so this outcome, this Nash equilibrium, even though it fits the definition of a Nash equilibrium, is not what we would call a subgame perfect Nash equilibrium. So let me just say that though this is a Nash equilibrium, there's another Nash equilibrium, and that is A choosing up and B choosing up. That Nash equilibrium is what we would call subgame perfect. So A choosing up and B also choosing up, this is a subgame perfect Nash equilibrium. And those are more important Nash equilibrium than this one, even though it's a Nash equilibrium, because it just doesn't make sense when you really think about it. If you were analyzing this problem, you would start to realize that this is a much more likely outcome than that would be. And the reason is that if B threatened to make this decision to choose down no matter what, A is probably going to say, you know what, I don't believe you. I don't believe that if I choose up and you're in this situation, that you're going to choose 5 instead of 15. And we can apply that. I mean, this is kind of like, you've probably experienced somebody doing this before. This is kind of like if your dad says, look, if you come home late tonight, I'm going to burn the car up. Okay, I don't believe that, right? If you actually stayed out late and then you came home and your dad actually did burn the car, well, that's highly unlikely. I don't believe too many people would do that. That's one of those threats that you make, and then after you make it, you realize, that's not credible. They're not going to believe I would not actually burn the car up. So that's kind of what's going down. That threat of burning the car up is not a sub-game perfect Nash equilibrium, because in the sub-game where your kid comes home late, you're probably just going to accept it. You're probably not going to actually burn the car down. We can think about this in terms of a game that would affect two businesses by thinking about what we would describe as the entry game. So if we had a game of entering, let's consider a market that only has a single firm. So let's suppose that there's a market with one firm, and that firm is firm B. And then we've got a potential entrant. So firm A is a potential entrant into the market. So they're not in the market yet. Here's what this game would look like. If we put firm A over here, then firm A gets to decide whether to enter the market or not. So let's suppose their two strategies are you either enter the market or you stay out of the market. I'm going to extend this one a little bit. Well, if firm A enters, then firm B is going to be at this decision node, and firm B has to decide, well, should we fight them or should we accommodate them? Fight or accommodate? Just grin and bear it. If firm A stays out, then firm B doesn't have a decision to make. There's no entry. So now we've got three possible outcomes here. So let's put some payoffs. Let's suppose that if firm A chooses to stay out, well, clearly they're not going to get any profit. And firm B, the firm that's already in the market, let's suppose they get 10 in profit. Maybe that's $10 million in a year. It doesn't matter. Let's suppose that if firm A chooses now to enter and firm B chooses to fight them. So firm B says, look, if you enter the market, we're taking you down. We're going to fight. We're going to flood the market. We're going to do whatever we can to make it bad for you. Then let's suppose if they do that, then the entrant gets -1 and the firm that's already in the market gets 1. On the other hand, let's suppose firm A enters and firm B just accommodates and says, okay, well, we wish you hadn't entered, but oh well, now here we are. Now let's suppose they split the market. They each get 5 in profit. So if there's no entry, the firm that's already in the market gets the 10. But if another firm enters and the firm that's already in the market just kind of goes with it, now they have to split the market, 5 each. Or the firm that's already in the market can say, look, you better not enter the market, because if you enter the market, we're just going to burn the place down. This is a situation very much like this, okay, where the threat of fighting is not it's not a legitimate threat. It's not a credible threat. Okay, so we're going to say that fighting is not subgame perfect. Fighting, not a credible threat. The likely outcome for this game is right there. It's a Nash equilibrium. So that would be an application of this type of multi-stage game. There are lots and lots of other applications of game theory, but that should give you a pretty good idea of how this would apply to making decisions if you're managing a business, whether it's a decision over monitoring employees or choosing price or choosing the quality of a product or entry into a market. So I'll see you in another video.